Today we are going to learn about the atomic structure, and in this chapter we will cover the following content, and these are structure of atom, identification of proton, neutron and electron, understanding the term atomic and proton number, describe the distribution of mass and charge, describe the behavior of beams of proton, neutron and electron moving in electrical field, and determination of the number of proton, neutron, and electron present in atom and in ions, and state and explain qualitative the variation in atomic radius and atomic ionic radius in groups and periods. So let's start first with the atom of structure. On the screen you can see that there is an experiment of Rutherford in which what are the experimental setup. First one is he selected a thin gold foil. Why he selected gold? Because gold is easily malleable into very fine sheets. Second one is fast moving alpha particles, and let me explain that what is alpha particles. Alpha particles are actually helium nuclei. Okay, when we talk about when we draw the structure of helium, it is having only one orbit, and in the nucleus there are two protons and two neutrons, and the electrons are rotating around the nucleus. So if helium atom lose these atoms, okay, so as a result what will happen that only this nucleus will remain having two proton and two neutron. This nucleus of helium atom is now called alpha particles. Alpha particles. And due to the presence of this proton in the nucleus, alpha particle having positive charge. Now, this is the experiment, and you can see that what was the observation, what were after, during this experiment. First one, that most of the alpha particles pass through the gold foil without any deflection from their original path. Second observation, a few alpha particles are deflected through small angles and few are deflected through large angles. And third one, a very few alpha particles completely rebound on hitting the gold foil and turn back on their path. On behalf of these, you can you can observe this by this easily animated diagram. This line of atoms are showing the gold foil, okay, and these are small particles are showing these are alpha particles. So you can see that most of the alpha particles are going straight, they are passing through the gold foil, okay, very few deflected from their original path, and very few rebound. So on behalf of these observation, what were the conclusion? First one, that as most of the alpha particles pass straight through the gold foil without any deflection, it shows that there is a lot of empty space in an atom. So this observation proves that most of the atom is empty. Most part of the atom is empty. Second one is some of the alpha particles are deflected through small and large angles, show that there is a positive center in atom which repel the positively charged alpha particle. We know very well that like charges repel each other. So alpha particles which are having a positive charge, when they reach near the nucleus of the gold atom, So they face the force of repulsion from the nucleus, and as a result, they deflected from their original path. Third one is that very few alpha particles completely rebound. Why they rebound? Actually, only just central part of the atom is very dense. So it is just like that. You are uh, striking the ball on a concrete wall. After striking the ball, tennis ball rebound. So in the same way, these alpha particles, when they strike with the very dense part of the nucleus, they rebound. Okay, the next content of this chapter is identification of subatomic particles. What are subatomic particles? Actually, the particles which are found in an atom are generally called subatomic particles, and these are electron, proton, and neutron. In this content, we will discuss about their relative charges and their relative masses. So first one, electron. Electron reside outside the nucleus. It rotates around the nucleus in an orbit, shell, or energy level, while proton and neutron are found inside the nucleus. When we talk about the charges of electron and proton and neutron, so we see here that electron having negative charge, and its charge is 1.60 into 10 to the power minus 19 coulomb, while the proton having the same charge but its charge is positive. So in this way we can say that proton and electron charges are equal, but they are opposite to each other, while neutron having no charge. So here, for our convenience, we do not take the actual charge. Instead of, we take the relative charge, and we take the relative charge of electron is 1 minus and proton is 1 plus. Now we talk about the masses of these particles. When we see the masses of these particles, uh, you can see here that actually proton and electron neutron masses are almost equal. Okay, there is a very little bit variation, but when we see the mass of electron, so we find that mass of electron is very less than proton and neutron. So we neglect the mass of electron when we talk about the mass of an atom. So we just take the mass of proton and neutron in an atom, and we neglect the mass of electron. How we can explain here? See this. Actually, when we talk about, let's suppose that aluminum, aluminum mass is 27. After losing electron, 3 electron, it becomes aluminum ions, but still its mass is 27, because of that there is no change in the number of proton and neutron in aluminum ion. So it means that it proves that atoms and ion masses remain same, because here we neglect the mass of an electron. So in the same way, when we apply this knowledge here for neutron, neutron mass is 17, and it gains 3 electrons and becomes nitride ions, but still its mass, sorry, neutron mass is not 17, its mass is 14. So after gaining these 3 electrons, still its mass remain 14. So it proves that atoms and ions mass are not different, they are same. Why? Because we neglect the mass of electron when we talk about the mass of an atom. Now the next part is atomic number and mass number. Atomic number of an element is represented by letter Z of an, and it represents the number of protons in the nucleus of each atom of that element. It means that actually atomic number is the identity of an element. It remains same. What does it mean that if atomic mass, I mean atomic structure diagram is given, then we will count the number of proton in the nucleus. On behalf of this number of proton, we will identify the atom of elements. So atomic number is fixed for each and every element in the periodic table, and this is the criteria on behalf of this atomic number. All the elements are arranged in periodic table on behalf of this atomic number. Next one, mass number. Mass number of or nucleon number represented by the letter A. It is defined as the total number of protons and neutrons in an atom, and it is represented by this. X is here is a imaginary element. Its symbol X is representing the symbol of an imaginary element, and the superscript represented by A showing that this is mass number, while the subscript showing by Z representing the atomic number. And you can see here that lithium, the superscript showing the 7, it's showing that it is a mass number, while this uh, subscript 3 showing the atomic number of lithium. Distribution of mass and charge. When we talk about distribution of mass and charge, so from the above experiment of Rutherford, we learned that actually the mass of an atom is totally concentrated on the nucleus, and this nucleus containing proton and neutron, while electron actually reside outside the nucleus, and it rotates around the nucleus. We have learned in the first content that most of the part of the atom is empty, and this nucleus is very smaller than the first, even with than the first orbit of an atom. And when we talk about the charges, I mean proton, it is found in nucleus, and proton having a positive charge, so it means that actually positive charge reside in the nucleus. So actually it is also called nuclear charge because of the presence of proton. So as the number of proton increases in the periodic table, when we go from left to right in the periodic table, we say that a nuclear charge is increasing because the atomic number is increasing. Neutron having no charge. When we talk about electron having negative charge, and these electrons are found in this way that they are reside in outside the nucleus in the orbit shell or level and sublevel, and also in orbitals. And when we talk about the mass, it is very important that actually when we talk about the mass of a nucleus is very dense. And imagine that if we any matchbox, its size is not much large, but if the matchbox is filled with only nucleus, then you can imagine that how the mass of this matchbox will be equal to 200 million tons. That is very large, showing the how dense a nucleus of an atom is. Next one, the behavior of beam in an electric field. When the particles of atom, I mean subatomic particle of an atom, they are sent in the form of beam through electric field, these particles are deflected. Okay, and see this here, neutron go straight because it has no charge, so it is not deflected by any I mean positive or a negative electrical field, so it goes straight through the electrical field, while electron is attracted towards positive end of the electrical field, while proton is deflected towards negative field. And see, this deflection of electron and proton are not equal. Reason is that we have earlier learned that proton and electron, their charge are same, but their masses are not same. So due to this reason, see this, the deflection of proton is less, while the deflection of electron is very much than the proton, because of it has very less mass. So okay, proton and electron are deflected because they are charged particles. The neutron are undeflected as they have no charge, while the electron is deflected more than the proton because it has less mass. Next one, determination of proton, neutron, and electron number. How can we find out these subatomic particles number? The criteria is that if the symbol of any element is given also with their mass number and the electron atomic number, with the help of these two we can find out the proton, neutron, and electron number. So atomic number can be find out. So what will be the atomic number of any element? It will be the number of proton of that element. So here atomic number is 11. It means that number of proton is also 11. So we can write here that number of proton is here 11. Number 2, to find the neutron, how can we find the neutron? Subtract the atomic number from the mass number. So if we are going to find out the number of neutron in an atom, then what we will do that we subtract the atomic number from mass number. The mass number is 23 and the atomic number is 11. So in this way we find out that this is the number of neutron of sodium atom. And the third one is electron. To find the electron in a neutral atom, write down the same number as the number of proton. So here the number, this is neutral atom showing no charge, so it means that it is an atom. So what is the proton here? 11. So electron is also 11. Next one, how can we find out the number of proton, electron, and neutron if it is not an atom but it is a charged particle which is called ions? So here see this, the criteria here. This is the symbol of an imaginary element. Its mass number is showing by A and atomic number by Z, and the Q showing its relative charge. So we know very well that the number of proton is an atom or ion is given by the atomic number. So this will be the atomic number, or this will be the proton number of proton of that element, and this atomic number is actually is the combination of proton and neutron. So what we do that for the number of neutron can be found by subtracting the atomic number from the relative atomic mass. And the third one, that the number of electron in an ion can be found using the atomic number, which is the same as the relative atomic charge of that nucleus, and subtracting the charge of the ions. How we will do that? Simply here, proton and neutron, we have learned that how we will find out the electron. We will find out in an atom by this one, that electron will be equal to atomic number, that is Z, and we will subtract the charge of that ions from atomic number. So in this way we will find out the number of electron in a charged particle. See the example of boron here. So the atomic number is showing the proton number. So here atomic number is 5, so the proton is 5 here. And this is showing the mass number, and we are going to find out the number of neutron. So number of neutron is find out by subtracting the atomic number from mass number. So mass number here is 11, and subtract the atomic number, it is equal to 6. And now the number of electron, because boron here is a charged particle, so what we do is that we subtract this charged particle from the atomic number. So atomic number minus charged particle, and the charged particle here I'm writing here for convenience that it is Q. So the atomic number is 5 minus the charge here is +3. So 5 plus minus minus 3. Now it will be 2. So this is the number of electron. Next one, in the case of oxide ions, here again atomic number is 8, so it means that its number of proton is 8. The mass number is 16, so we can calculate the number of neutron by subtracting the atomic number from mass number. So atomic mass number is 16, atomic number is 8, so the number of neutron we get is 8. And electron, the last one, electron as usual, atomic number minus charge. So here atomic number is 8 minus the charge is also -2. So it means this 8 and minus plus. So see this, the number of electron is 10 now. So remember that if any charge particle having positive charge, its electron will be always less than the proton. But if the charge particle having negative charge, so its electron will always be more than proton. Now the next one, atomic and ionic radius. The atomic radius is the average distance from the center of nucleus of a neutral atom to the outer boundary of its electron shell. For isolated neutral atoms, the atomic nucleus ranges from 30 picometer, uh, which is equal to trillionth of a meter, and uh, 300 picometer. This is the total distance between all the elements. It starts from 30 and up to 300. The largest atom is cesium. Remember that when we look at the periodic table, in group 1, we find out that there is another element uh, behind cesium, that is francium, but we do not discuss the francium because it is a radioactive isotopes, so we do not discuss it. So here we mentioned that cesium is the largest atom, while the smallest atom is helium, and these actually are saying because of their uh, atomic radius. So see this is the simple animated diagram figure by which you can realize that how these atomic radius are changing when we are going across the period from left to right, or when we are going from in a group from top to bottom. So by looking at this animated diagram, we can easily learn that across the period atomic radius is decreasing, while uh, in the group from top to bottom atomic radius is increasing. These are the measurement of some element given here, their atomic radius. Now see this we have to discuss that why there is an increase in atomic radius here. Atomic radius is increasing just because of that when we go from left to right in a periodic table, we see that nuclear charge is increasing. The number of proton are increasing in the nucleus. So as a result, we know very well that proton attract the electron in outermost shell. So as the number of electron are increasing, so the force of attraction for outermost shell is more. And we know very well that in a period, number of orbit does not change. What does it mean? That see this in case of first period, the number of orbit in hydrogen and helium is same, which is only just one orbit. So here in hydrogen there is a one proton in in nucleus, so electron is attracted by the nucleus proton. And here helium having the just one orbit, just like hydrogen, but here in the nucleus there are two protons, and these two protons are attracting outer shell electron with more force of attraction. As a result, helium atomic radius is less than hydrogen atom. So same case with we see in the other periods, like second period or third period and so on. And when we talk about the atomic radius in group, see this in the group, although atomic nuclear charge is also increasing in the group, but here there is a one more thing involving here, and that is in the group number of orbit are also increasing down the group, showing the more shell. And due to the more shell, the outer shell electron are attracted by proton of the nucleus, but also they face the force of repulsion of the inner orbit electrons. And as we go down the group, the number of orbits are increasing, so the outer most shell electron face more repulsion as the number of orbit increasing in an atom. So that's why the force of attraction between proton and electron, outermost shell electron, become weaker. So that's why the atomic radius increases when we go down the group. Next thing is ionic radius. When we talk about ionic radius, so there are two types of ions. One is a positive ion, while the other one is negative ions. Periodic table trends. What does it show? See this, atomic and ionic radius increase moving down a group or column of the periodic table. This is because atom gains an electron shell. Atomic and ionic radius generally decrease moving across a period or row of the periodic table. This is because the increasing number of protons exert a stronger attraction to the electrons, drawing them in, in more tightly. Noble gases are the exception of this trend. The size of noble gases atom is larger than the halogen atom that precede it. Now, cations or positive ions. So if the ions are positive, so an atom loses one or more electron when it forms the cations, making the ion smaller than the neutral atom, while anions or negative ions and atoms gains one or more electron to form an ions, making the ion larger than the neutral atom. So you can see here that although the nitrogen, oxygen, and fluorine, they are second period element. After gaining electron, they becomes nitride, oxide, and fluoride ion respectively, while the sodium, magnesium, and aluminium, they are the third period element. And after losing electron from their outermost shell, they become sodium ion, magnesium ion, and aluminum ions. So when we see their, radius, we find out that still you can check the difference between these ions. Although the nitride, oxide, and fluoride belongs to second period, but their ionic radius are larger than the ionic radius of sodium, magnesium, and aluminum ions, which belongs to third period. Just because that after losing electron, sodium, magnesium, and aluminum ions, they also lose their outermost electron. Their outermost electron is finished. So as a result, their radius is also, uh, decreases. Now the next content is isotopes. What are isotopes? Isotopes are atoms that have the same atomic number but different mass numbers due to the different number of neutrons they contain. There could be two or more isotopes that fall under the same atomic number. So see here that there are three isotopes of lithium, and all these lithium having the same number of proton, which is three. Okay, and when we subtract the atomic number from mass number, we uh, obtain the neutron. So here in the first one, neutron number is 3. In the second one, neutron number is 4. And then in the third one, neutron number is 5. So here, see this case, these are the 3 atoms of lithium, and they all having the same number of proton, but their neutron numbers are different. So that's why they are called the isotopes of lithium. Now the next one is notation for isotopes. How we will express this notation? How can we symbolize this notation? So isotope notation is used to visualize and discover what an isotope's mass number is, as well as the number of neutrons, protons, and electrons an isotopes contain. So isotopes notation contain the mass number, atomic number, and charge if there is one. Since isotopes have the same atomic number, it is also common to omit the atomic number from the isotopes notation. So see this here, when we talk about isotope notations, see here that this is oxidine, and it is having, I mean, atomic number 8 and mass number is 18. So in the next one, because the atomic number is same for all the isotopes, so here atomic number can be omitted from the symbols. And remember that the charge of isotopes, any isotopes, okay, will not, change its chemical properties, because in a chemical reaction electrons are involved, so they are loss or gains, or in some cases they are shared with each other. So the chemical properties of isotopes remain same, but their physical properties are different because just of the increase in their mass number. So this is the isotope notation of oxidines, showing that it is oxidine having a negative charge. So the number of proton here is 8, and the number of neutron can be found out by subtracting this atomic number from the mass number. So 18 minus 8, it is equal to 10 neutron. And when we talk about electron, so again we will apply the same formula, that atomic numbers minus charge. So atomic number is here 8, so minus, when we subtract this, so minus minus plus, so it becomes 8 plus 2, it becomes 10 electrons. So this, in this way we find out the electron, proton, and neutron from isotopes notation. And in the last, a neutral atom has the same number of electron as proton. Thus, different isotopes of a given element all have the same number of electrons and share a similar electronic structure, because the chemical behavior of an atom is largely determined by its electronic structure. Different isotopes exhibit nearly identical chemical behavior. That's all, and I hope that you will find out helpful this video. Inshallah, in the next video we will discuss the other content of the atomic structure. Thank you.